Thank you for giving me the opportunity to present our results. So this is a joint work with my both co-directors and Rouly Zhang, which is a PhD student with Jean-François, who did a good part of the code. So a part of the credit is obviously for her. So the context we're working with is to try and build meshes for high order numerical schemes. So nowadays, body-fitted curved meshes are already well in use to accurately capture the geometry when you use high-order schemes. Otherwise, you degrade your convergent order. So the idea for this work is very simple. Is why not also use curved meshes inside the computational domain to represent the solution, not only the geometry, but also the solution. So with this idea, we'll try to build meshes of what we call P2 triangles, so triangles with parabolic edges that are adapted to a numerical solution U that can come from either finite element or finite volume methods. So we're going to work with parabolic edges, and we're going to restrain ourselves to the case where the mid-edge point is on the orthogonal bisector. So this is a choice this is a bit of a compromise to have a decent how do you say that to save some time and also have curved elements. So this yields the following parametric equation for the curve for x in function of x1, x2, and the midpoint the midpoint. And we'll try to minimize the edge length to approach to get the parabola as close as possible to a geodesic in the metric field while using a golden section search. So we'll try to determine the height alpha prime, such as it minimizes sorry the length of the curve in the metric field, which I will describe in a second. So we have to first define the metric field for the function we'd like to approach. So the choice we made is the following. We try to match and follow the solution as best as we can. So the principal directions for the metric field are going to be first the gradient of the solution and the isoline of the solution, because obviously along this direction the solution doesn't change. And if we can build elements that perfectly follow the isoline, then the solution is constant on this element. To determine the sizes, we're going to use a posteriori error estimate. So this is a priori error estimate in which we're going to plug our a posteriori error estimate based for the derivatives, I mean. So we like to redistribute the interpolation error over the edges of the mesh. So we have this following Taylor remainder terms when we estimate the error between the real function and its P2 Lagrange interpolate. It is a function of the third power of the edge length that we're looking for. And it involves the third order derivatives and the Hessian matrix of the function. So while calling all this term the error along both directions we consider, we can determine the element size by computing by plugging in the target error we'd like to achieve on the edges and on computing this error term. So to compute this, we obviously need to recover some high order derivatives, the third order derivative tensor and the Hessian tensor / matrix. So we use the the Zhang and Naga method that was already presented by André Fortin and Marco Picasso in the previous talks, which they call themselves the polynomial preserving recovery, the PPR, which consists of finding first a recovery of the solution, which is of one order higher than the finite element solution. So we obtain this solution on patches of elements by solving a local least square problem, and we approximate the gradient of the solution by the gradient of the recovered function at the vertices that is weighted by the shape functions. So to recover the Hessian and the third order derivatives, we just apply this process 2 or 3 times. So successive PPR and then derivation to recover the higher order derivatives. Now that you have we have the metric field and the derivatives, we can I can point out the meshing algorithm, which consists of 5 parts. The first is going to be to insert the points inside the domain. So we start by the input of our point insertion algorithm is a queue with all the points that we spaced based on the metric field on the boundary. And we have also the metric field on the domain. And then we are going to spawn points that are going to be within unit distance from one another along the principal directions of the metric, while also checking that they are not too close to the other already added points. So we're going to add to a queue, we're going to spawn the points along the 4 directions of the metrics. Well, so plus and minus both principal directions. And we keep them if they are not too far from points are already added. So this way we ensure that all the points we insert are within a distance 1 over square root of 2 and square root of 2. So this is our definition of a quasi-unit edge. So that we make sure when we are going to connect those points, they will form edges that are within this interval and hence are called quasi-unit. Once we have generated our points, we connect them first in an anisotropic fashion. So we use, for example, a constrained Delaunay triangulation, and then we swap the edges until the anisotropic Delaunay criterion is satisfied. So we obtain this kind of mesh. And then we are going to curve all the edges one at a time. So as I explained before, we are going to determine the optimal alpha in our definition of the parabolic edge, so that each straight edge becomes an approximation of the geodesic in the metric field. What we have to be careful at this point is not to generate invalid curved elements. So elements with the Jacobian of the transformation that goes to 0 becomes negative. So to do this, we have sufficient condition that was developed by a former student of Jean-François. So we can very quickly check if an element is indeed invalid or not, and we can backtrack to the previous configuration with a different alpha where we are sure that the element was valid. And this is a process that always ends well, because the limit case is which is also the worst case, is when we revert to the straight edge triangle, which is by definition valid. So once we have curved the initial anisotropic mesh, we can do a bunch of edge swaps to improve the quality of the mesh with the 2 criteria that the edge swap must yield, of course, valid triangles. So the new triangles here and here must be valid. And the worst quality has to be better than the worst previous quality. So we make sure that we are successively improving the quality of the mesh. And here we have defined the quality measure with respect to the metric field. So it's essentially a measure of the area of the triangle divided by a function of the length of its edges. And that's normalized by the measure of the ideal triangle. So this operation allows to improve the quality of the mesh, but it can sometimes stumble into local configuration that we cannot move from to further optimize the mesh. So to this end, to solve this, we introduce what we call the curvilinear SPR, small polygon reconnection, which is inspired from a straight edges SPR. And it's essentially a way to consider cavities of sets of triangles and enumerate the possible triangulation of this cavity, compute all the quality of the triangles, and choose the local triangulation that achieves the best minimum quality from among all the possible triangulations. So when the elements are straight, it's it's easy to actually tabulate all the triangles. So here there would be 20 distinct triangles and compute and pre-compute their quality. But when we use, when we generate curved edges, we don't know beforehand what will be the triangle. And so we have to recompute the quality. So this is a bit slower as an operation, but it allows to take a bit of, to have a bigger view on some areas of the mesh and to further improve the quality, whereas edge swap are not able to achieve this result. So for example, here, I mean, we need cavities. We need cavities to examine and to enumerate the triangulation. So how do we build those cavities? Well, at first, there are two ways. First, we either pick a unit edge or close to unit edge that should be in the mesh, but that is not at this point in the mesh, like this one, because it was swapped during the edge swap process. And we consider all the triangles that are intersected by these ideal edge, and we build a cavity out of these 3 curved triangles. And then we enumerate the triangulations, we evaluate the qualities of the triangles, and we choose the best triangulation. So this is done first for this geodesic. And in this case, this will be done again for long edges that are beyond the square root of 2 bound that we impose to be within the quasi-unit interval. And we do the same thing. So we take all the triangles that are connected with this long edge, and we form a cavity with those triangles to yield this configuration. So yeah, 2 ways to build the cavities. One, you take a unit edge that should be in the mesh and take the intersecting triangles. And the other is you build a cavity from triangles connected with a long edge. So this is an example of the algorithm on an analytic function. So for example, we solve a diffusion problem with this function as the solution, and we get a manufactured source term. So this is the final mesh, and this is the Jacobian on all the triangles. As we can see, they're all valid. They're all greater than 0. And the worst case are, for example, these 2, which are quite symmetric, and the Jacobian is the order of 0.2. So do we indeed, yeah, I forgot to mention it in the beginning, but the aim is to lower the interpolation error between, to get a better interpolation error that we would have when we compare it to an anisotropic mesh. So in this case, this is indeed achieved, because we get first we get the same convergence rate, which is to be expected, but also we are lower compared to a straight-sided anisotropic mesh, which is good news. This is especially the case when we have a low number of elements, because there are more benefits to curve the mesh if you keep the complexity of the mesh low, whereas if you go higher and higher in complexity, the anisotropic mesh start having a comparable interpolation error, and there's no real gain from going curved when you increase the complexity of the mesh. So another test case that we made is the Taylor-Green vertex. So we solved this stationary Taylor-Green problem, and we obtained those kind of meshes with 2 different target error along the edges. This is for 2 different kind of errors on the U velocity field. This is an example from the advection of a bubble of tracer that is put inside a fixed velocity field. So this is the evolution of the mesh. We can see that it follows the solution nicely. But as I said, if we go higher and higher in complexity, this along the curves of the solution, yes, it is curves, but it's not that different from anisotropic. So I should probably rerun this example with a lower complexity to have more benefit from going curved. And the last example is the flow past the cylinder at a low Reynolds number. So we can see that the elements do quite follow the isolines of the solution again. So yeah, this is very much still a work in progress, as you might have observed. What works so far is that the meshes are indeed curved and they do follow the metric field, which is good news. The meshes by construction, they only contain valid elements, and we observe an improved interpolation error when the complexity of the mesh, so the number of vertices is still reduced. So this is the real threat to going curved, is if you can achieve, if you can follow quite nicely the solution with a low number of vertices, then yes, there is a clear improvement on the interpolation error. But as there are more and more elements in the mesh, the difference, the gain when you compare to an anisotropic mesh is a bit reduced. The drawback is, for now, it's slow. It's been coded in quite a naive fashion, and that requires to evaluate a lot of the metric field when we compute some integrals. So it has to be improved, and we also have to carefully choose the basis functions we use on those meshes to maintain their convergence order. So yeah, thank you for your attention. That's it for me. Thank you.